In this particular video, we will be looking at two concepts: removing the last set bit and counting the number of set bits when you are given a binary number. Hello friends, welcome back to my channel and my mini series on bit manipulations. Basically, what we are trying to do over here is leverage all of these bit manipulation techniques so that we can write a faster code. And the best part is all of these bit manipulation techniques are programming language independent. That means no matter what language do you choose, Java, Python, C, C Sharp, C++, they all work the same. The bitwise operators are available in every programming language and they work efficiently. I am going to build upon the concepts that I have already discussed. And we are going to take the advantage of the logical AND operator and also how do you represent binary numbers? How do you represent n minus 1, n plus 1, all of that. So if all of these things feel pretty new to you, I would highly recommend you to check out my previous videos first. Otherwise, let's get started. You can call it a concept or you can also look at it as a problem statement. Basically, you are given a binary number and you have to remove the last set bit. So for example, this is a binary number. And when you talk about the last set bit, how do you look at that? You start from the very right and then you try to check, okay, which bit is set. If it is set, it is 1, otherwise it is 0. So going from this direction, this is the last set bit, or you can also say the first bit from the right. What you have to do is you have to clear out this bit. So the result should be something like this. You can notice that the entire number remains same. Only this bit has been cleared. Similarly, let us look at the second test case. I have this number available and you have to remove the last set bit. Or starting from the right direction, you need to remove the first set bit. If this becomes 0, what is your answer? This should be your answer, right? And that is what I'm expecting. Similarly, if you have something like this, I check the last set bit, the first bit from the right side. And this in fact is the only set bit in this number. If I set this to 0, what will happen? This will be my answer. I will get an overall 0, right? So that is what the problem statement is asking you. And notice that all of these are given as decimal numbers or binary numbers. It could be anything. For a moment, let us consider the fact that these are all decimal numbers given as an input n. You have said that, okay, I will give you a number n. It could be anything, 57, 56, anything. And you have to remove the last set bit and return me whatever the answer is. In this case, we are also expecting that, okay, we are going to return a decimal as the answer. Mostly in these problems, you are given only a decimal number and then you have to work upon it, do any calculations that you have to do, and then return back the decimal number however you want to. Now, before we attack this problem, there is another interesting concept that you need to learn about. That is, if you are given a number n, how do you find out n minus 1 in binary? So basically, let us say you are given all of these binary numbers. If you are interested in the decimal representation of these numbers, these are just actually 40, 58, 8, and 27. And I am asking you to tell me what will be the binary representation of the number 39, 57, 7, and 26. I know you can just use the traditional method to keep on dividing by 2 and find out the binary representation of all of these numbers. But finding the n minus 1 binary representation is not that tricky. Basically, you just have to follow certain rules. The first rule is that you start from the very right. And then you keep on going to the left until and unless you encounter the first set bit. I found this out to be 1 over here, correct? What you need to do is convert this to 0 and then start going back, and whatever zeros do you find, you need to convert them back all to 1. So once again, I start from the very back. I go all the way up till I find the number 1. Then I convert it to 0 and then I convert all the remaining numbers to 1. So once I do that, what will happen? I will write it down as 1, 0, 0, 1, 1, 1. Once again, notice what happened. I started from the very back. I went 3 places. I found a 1. I converted it to 0. So I have 0 over here. Now, starting from here, I traverse back, take all these three numbers and convert it to 1. And that is it. This is the binary representation of 39. Let us look at 58 now. Follow the same technique. Start from the very right. Start going left until you find a 1. You found it. Convert it to 0. Go back and convert all the remaining elements to 1. So this will translate to 1, 1, 1, 0, 0 and a 1. Notice this got converted to 0 and all the remaining numbers got converted to 1. Similarly, for the case of 8, I start from the very right, go to the left, I find a 1, convert this to 0 and then start moving all the way back. So I will get 0, 1, 1, 1, which is equivalent to 1, 1, 1. So this is the binary representation of 7, right? Similarly, let us look at one more example, that is 27. And as soon as you start, you will find a 1 over here. Follow the same approach. Convert this to 0 and then start going back. You don't have any other ones, so you stop. So the binary representation of 26 will be 1, 1, 0, 1 and a 0. This is how, if you are given a number n, you can find out n minus 1. Now, why are we doing all of this? The interesting part about bitwise operators is, if you look at a number n and you try to compare n minus 1 and n plus 1, you will get some results, right? The interesting part happens when you try to perform logical operations upon them. You will start to see patterns over there. So let us go back to our problem statement. I had these three test cases available. These are my numbers and this is how you represent them in binary. If you now have to look at n minus 1, so for example 39, 57 and I am looking at number 7 over here. How will you represent these numbers? Once again, I write down 0 here and then 1, 1, 1, 1, 0. Doing this, I write down 0 here, 1 and then 0, 1, 1, 1. For this also, I write down 0 here and then 1, 1, 1. This is how I have represented these numbers. Now, if you notice, what did we do? This section remains the same, but this other half, this is where the magic happened. Similarly, this entire section up till the last set bit, this remains the same, and this is where the magic happens. Once again, all of the section until the last set bit, it remains the same, and this is where the magic happens. And what is the problem statement asking you? You have to remove the last set bit. It means you don't have to do anything up till all the bits up till the last set bit, correct? So amongst all of these test cases, the part until the last set bit, it is unchanged, right? It means we are heading in the right direction. Now, what do you have to do? You have to remove the last set bit. And notice what happens in the second part of all of these numbers. This is where the last bit and its numbers come in handy. Notice that all of these have flipped. So, if I perform an AND operation on all of them, what should happen? All of the numbers up till the first set bit, they should remain the same, correct? So, when I am doing an AND operation, is this the result that I'm gonna get? Notice, 0 and 1 will give you a 0, 0 and 1 is a 0, 0 and 1 is a 0, 1 and 0 is a 0, and this part remain unchanged, so I have 1, 0. Similarly, 0 and 1 is a 0, 1 and 0 is a 0, and this entire part remains unchanged. Similarly, for the last test case, 0, 1, 0, 1, 0, 1 gives you 3 zeros, 1 and 0 gives you a 0, and whatever was the last part, that remains unchanged. So, I easily got my answer. What did we just do? If you notice closely, that is all we did. To get the answer, we took the number and we used a logical AND operator with n minus 1. That is it. You can see how efficient your program becomes. If you try to approach this particular problem in the traditional way, you will be writing for loops, converting numbers here and there, and then you will wonder, okay, why is my program slow? Why am I not in the top percentile of the problem solvers? That is the reason. because bitwise operators help you to perform your program very, very efficiently. Apart from efficiency, you might not notice that when you solve a particular concept, you are unlocking other problems as well. For example, in this particular problem, what did you do? You took a binary number and you removed the last set bit, right? So what happened? You were given a binary number with zeros and ones, and after one operation, what happened? One of the bits that was the very last, that got unset, right? So can you think about another problem statement where you need to find out the total number of bits that are set? Over here, let us look at this problem statement and you will soon realize how similar it is. I am given these two particular numbers, and once again, they are usually represented as normal decimal numbers. So you will be given a number 48 and you will be given a number 58. And you will be asked, okay, find the total number of set bits. The traditional method is, okay, you are gonna perform a for loop, do divide by 2 and find out the binary number and all sort of those things. But what happens if you try to use the same concept that we just discussed? Over here, this number is represented by n. If I have the number n minus 1, how can I write it? I can write it down as 1, 0, 0, 1, 1, 1. Now, if I do an AND operation on them, what will I get? I am gonna get 1, 0, 0, 0, 0, 0. That is what we did, right? We took the last set bit and we cleared it out. But notice, what do you see amongst these two things? With one operation, what did you do? You removed one set bit. And what is the problem asking you? Count the number of set bits. If you perform this operation one more time, so what I'm saying over here is, if I take up the number n minus 2, what will you do? Once again, you start from the very right, go all the way till you find a set bit, turn it to 0, and then convert all the bits to 1. Once I do that, I get 0, 1, 1, 1, 1, 1. And then if I AND it, what do I get? I get 0, 0, 0, 0, 0, 0. So after two such operations, I was able to set all of the bits as 0. And how many bits did I have set in the original condition? There were 2 bits. So does that give you an idea? If you run a for loop just to clear out bits until your number becomes 0, then you will be able to count the number of set bits, right? Let us look at another test case. I have this particular example, right? You can see that it has 4 bits set. So we're going to start off with the traditional way. I will find out n minus 1. So that will be 1, 0, and I copy all of the rest. If I do an AND operation, what do I get over here? I will get 0, 0, 0, 1, 1, 1. I have unset 1 bit. Let me repeat the process because this number is not yet 0. So n minus 2. So once again, this will be 0 and 1, 1, 1. This remains the same. And now I will do an AND operation. As soon as I do an AND, I get 1, 1, 0, 0, 0, 0. After 2 operations, 2 of my bits have been unset. If I perform the same operation again, 1, 0, 1, 1, 1, 1, and that is n minus 3. As soon as I do an AND operation, what will happen? 1, 0, 0, 0, 0, 0. So after 3 operations, 3 of my bits have been unset. And you can easily guess, if I do one more operation, then this entire number will become 0 and I can stop. It means I need to just continue doing this operation until my number becomes entirely 0. You will be surprised how small the code entirely becomes. Can I say like this? I initialize my counter to 0, right? Now I need to run a while loop until my number does not become equal to 0. And what do I do in my loop? I say n equals to n logical AND of n minus 1. So what happens? N logical AND of n minus 1, and I assign this back to n. And at the same time, I do a counter plus plus. So I get 1 count. Now what will happen? This number is still not 0. The loop runs again. And once again, I do a logical AND with n minus 1. So I get counter plus plus, count becomes 2, the number is now 0, and this loop ends, I can return my counter. Similarly, for this case also, you can try to work it out. But what I'm trying to say over here is, this method, using bitwise operators, you can notice that it is not directed towards any particular language. These bitwise operators work with every language that you can use. Whereas if you were trying to write the code in a traditional method, then you need to understand, okay, this is how I write a for loop in Go. This is how I write a for loop in Python. This is how you maintain your variables. But using bitwise operators come in really handy, and they can actually speed up your performance. And this is where I would like to stop for now. Take a moment to digest all of this and try to understand what was happening. Try to take up some examples on your own and try to understand how you are able to clear a bit. Can you work out a case where you want to set a particular bit? Can you work out a case where you want to set the rightmost bit or the leftmost bit? All of these things can help you understand bitwise operators, and rather they can help you to write even faster programs. Just tell me everything in the comment section below, and there could be also some tricks that I haven't discovered. It will become a very good knowledge base, and I would also like to learn from all of you. If you found all of this content helpful, please do consider subscribing to my channel, as this really keeps me motivated and I can make more such content. Also, a huge shout out to all of the members who support my channel. You guys really keep me going. And as a member, you do get priority reply to your comments and early access to new videos as well. In my upcoming videos, we are gonna again take the application of these concepts and build new things on top of it. You might already realize that this is a compounding effect. The more you learn, the better you will code. So stay tuned for my upcoming video. Until then, see ya.